Cool, thank you all for coming. There are still some seats here. If you want to take a seat instead of standing in the back, then feel free to do that. No need for you to stand. There are still 1, 2, 3, 4, 5, 6, 7 seats. I want you to be comfortable and enjoy yourself because this will be a lot of content. This will be a fire hose of information. And I just want to warn you up front. You don't need to remember all the things I say immediately. You don't need to write anything down. You'll get the slides. And this is more to show you what's there and to remember, oh, this guy talked about this thing which could help me. And then go look it up for real and find it out, right? So don't expect to remember all the stuff because it will be a lot, right? So, and actually it says 10 tips, but each of these 10 tips of course has like subsets, so it's perhaps like 100 or so, or no, perhaps not 100, but 50. So, cool, welcome for being here. I'm really glad and happy because this is also something that's really close to my heart. I've been with Neo4j for 12 years. I was there when Cypher was born and created, and we had a lot of fun adding it. And actually, I remember it a little bit differently from Jim. It was not Visio that triggered the pattern syntax, but it was actually people sharing graph patterns in email. So when you write an email and you want to talk about something relates to something, they actually use the round parentheses and the ASCII art arrows, and that's where we got it from, because lots of discussions around graph models happened like via email or Usenet groups back then, or our Google group, and so basically people put just their graph model into these ASCII arts, and that's where actually the Cypher pattern syntax came from. What's true about the Visio bit is that it basically resembles what you draw on a whiteboard, right, in an ASCII art manner. Okay, going into it. Why should you care about Cypher's or Cypher optimization and Cypher tuning and things like that? So one is of course efficiency. You want to have your queries run as fast as possible, right? The other thing that these tips should help you with is readability. So there are some features in Cypher where you make it more concise and more readable. So you don't have to be as verbose and spell out a lot of things because they're like shortcuts and shorter syntaxes for things. It's also about resource usage. So how much memory, how many CPUs are basically pulled while running your query. And that's something where you basically can optimize for that. And the last one is about network transport. So the less data you transport over the network, the better it is. So for instance, instead of repeating one column like a million times with the same value, you can just create a document structure or a nested structure and return a nested structure as such. So that's kind of four things why you should care for this. So we're using data from Stack Overflow today. Fortunately, Stack Overflow publishes all their data as a data dump. You can get it from Internet Archive. And I have a load script that can load this into Neo4j in like 3 minutes or so. You get all of the Stack Overflow into Neo in 3 minutes, which is really nice. And so data model is really simple. You have users that post questions. Other users post answers to questions. And then questions are tagged with tags. So there's also comments, but I left out the comments because usually they don't add so much to the data. And I chose this data set because it's not tiny and it's not a toy data set, but it's really big. So you also see the impact of slow queries basically quite visibly. Cool. Let's get started. So I'll switch between the PowerPoint and my browser as such to show you actually the stuff in action. Let me just look at the time. So I think we have until 11. Let's see how far we get in this. So first one is profile. If you have never seen profile or explain in a Cypher query, this is something that's really useful because it allows you to peek behind the scenes and see what actually the Cypher execution engine is doing with your query. While you might expect it executes it the way that you write it, it actually takes this thing, looks at it, and determines based on database statistics, index selectivity, and other things, how to rewrite your query into something more efficient. And sometimes it's smart about it, sometimes it's not so smart, then you could help it by changing your query, but profile in query plans is something that's really nice. So if we look at, our browser here, it's really nice because PowerPoint, for whatever reason, always changes the mirror settings to not mirror. I don't know how to get rid of that, actually. You know what I'm gonna do? This PowerPoint thing annoys me a little bit. I just export it as an PDF because I don't want to deal with PowerPoint today anymore. Save. So you also see my beautiful German setting here. Oh, sorry. Screen mirror. Come on. So, mirror. Okay, so this is our data set. You see, let me make it a little bit bigger. Can you read it in the back there? Is this okay? Cool. So this is our data set. So you see we have 50 million nodes, 120 or 51 million nodes, 124 million relationships. And if I call DB schema visualization, we should see an approximate visualization of the schema. It's a little bit messy. But you have the user who posts because this is kind of a multi-label thing. So let me just move this one. So a user posts questions, which can be answered by an answer, and then there's also an accepted link for the accepted answer, and then there are tags where the question is tagged with a tag as such. So that's kind of the basic data model as such. So if you're going to write a query like this one, so the question is, let me just open this and go into. If you write a question like this, or the question here is, what is the number of questions that a tag has, right? So you know, Stack Overflow has a lot of tags, and what is kind of the what are the tags that have the most questions? So in simple version that you would write is something like this. So let's just type this out real quick. So we match our tag. We have a question that is tagged with this tag. And we would say return t.name, count q or count star as questions, order by questions descending, limit 10. Right? So this is our query, and if we prefix this with explain, it actually shows us the query plan, how the engine basically estimates this to happen. So you basically see the different operators in Cypher. So this is doing a label scan. So it scans over all the tag labels. Then fetches the name for the tag as well. Then it expands over all the queries. You see it expands over almost 50 million relationships here. Then collects all the queries into an aggregation. The count aggregation here, and then does sorting and limiting, right? So explain only gives you what the planner thinks will happen, and when you run profile, it actually executes the query. So explain is actually also really nice when you want to see if a query is correct that you've written, and you can just run it with explain to check it. So for instance, imagine you have a bunch of scripts that you need to validate that they're actually valid Cypher, or you update the Neo4j version and you want to check if they're still valid, then you can just run all these statements through explain, and it will be really quickly, and the planner will, so the parser and the query planner will tell you, okay, there's an error or there's no error, which is actually quite nice. This is also what browser uses when they show these kind of little squiggly lines and warnings. Basically, behind the scenes, it actually sends an explain query to the back end, and whenever the explain sends a warning back, browser shows it as the squiggly line. So now if you run this query for real, it generates actually, what is this, 49 million DB hits. So a DB hit is not exactly one database read, but it's kind of a unit of a database activity. So it could be something like a property read, an index read, and a relationship read. It could be something like accessing something from the page cache and so on. So you have in the query plan also things like how much memory has been allocated for this operation, how many page cache hits or misses have happened. So this can also indicate when your page cache is incorrectly sized. So yeah, if you get a lot of misses, that means the database has to basically constantly reload stuff from disk because it doesn't have enough memory for keeping the active live set of data current. So then increasing page cache is really good. Otherwise, you're just measuring your disk performance, which is also not so useful, right? And then it's what the planner estimates, how many rows come back. And then actually in these kind of white bars in the Sankey diagram, you see how many rows were actually produced by each operation. These rows are really important because they affect the cardinality. So your query, while it's executed, has a certain cardinality, kind of the number of rows that are currently being processed. And you have to multiply the cardinality with the cost of an operation, right? So the more rows you have, if you have like an operation costs like 10 dB hits and you have 10,000 rows, then it's 100,000 dB hits, right? So the challenge is either get the cardinality down or have a fast operation, either of which can help you a lot. And the benefit of running profile over explain that it shows you the actual operation, the actual results, so the actual dB hits, the actual rows, and also the actual page cache hits and misses as well. So, and I use profile a lot if someone from a customer or field or community member comes with an interesting query. I always ask them, send me your profile output, because only then, I mean, you can send me their query, but if you don't have their data, you don't know, do they have like the right indexes set up, what's kind of their setup in terms of page cache and so on. So just looking at the query, sometimes you can give them hints, but usually it's good to get kind of this profile information. So if you ever get asked to help with optimizations, always ask for the profile output, right? And so that's kind of our first foray into this. What else did I want to say for profile? Yeah, so in general, you should avoid stuff that has eager in its name if you want to really push through a lot of data. So there are two kind of eager operations. One is aggregation. You can imagine if you have to aggregate, it needs to pull in all the results to aggregate them into buckets, basically, right? So that's one operation where it can't stream basically all the way from the database to the client. Usually what Neo4j and Cypher and the Bolt protocol and the drivers try to do is, as data is fetched from the database during the query, it's actually streamed through like a hamster wheel, basically all the way to the client. And if your client is also doing processing in a streaming manner, then actually in between no extra memory is allocated, which is really, really nice, because then you have like just a stream of data coming directly basically from the database's memory into your client as such. So that's really cool. Sometimes you need to aggregate, that's also fine. The only thing that you have to watch out for, if you aggregate large volumes of data, that takes a lot of memory as well, right? But if you just do a count, that's not a big deal. That's pretty straightforward. The other eager operator, I'll say a little bit about this later, is something where Cypher needs to be correct, where correctness is actually valued over performance. When you mix a read and write operations, and when actually the write operations would affect the read operations. So imagine you're matching for, let's say, user nodes, and as a result of the match of the user nodes, you're creating new user nodes. So if you kind of construct your query in an unlucky way, then you create an endless loop. So you do a perpetuum mobile, because you're creating more users as you find users, and that would just blow up into an endless loop. And that's why Cypher inserts this kind of eager operation, which says, after the read, I fetch all the reads, and then I start doing the writes. But it also means it has to allocate memory for fetching all this data, basically. And that's why, especially if you do imports and inserts of large volumes of data, like let's say 10 million or 100 million records, if it reads like the 100 million things into memory first before it starts writing the first record, oftentimes this is something that doesn't go well. That's why batching updates into smaller chunks, also from the client side, just sending 50,000 records at a time is usually better as well. And you can parallelize it as well. Okay, so much for profile. Next one is properties. So in Neo4j, property reads are more expensive than they should be. I would love if you had a better property storage that is faster, but it is what it is. And so you should avoid properties reads to the last moment possible as such, right? So for instance, imagine you're pulling let's say 10,000 nodes from your database, then you're doing some sorting, limiting, but you're actually only returning 100 of these 10,000 nodes. But if in your Cypher query you access properties of these 100,000 nodes early on, then Cypher has to read these 100,000 properties from the property store, even if you're just returning 10 or 100 nodes. So that means if you can defer the property read after you have applied the limit, then this helps you a lot, right? So that's, for instance, something that's really nice. And one place where people often don't see that they're actually pulling properties as aggregations. So in our example, if I rerun our example with a slight change, so here you see actually it's pulling the name and does the count aggregation, right, to return it. So that means when it does the aggregation, it says t.name is our aggregation key. So that means it has to fetch the aggregation key basically 50 million times from the property store, right? It does some caching, but it still has to access it. But what we know is actually, of course, the tag name is unique, but so is the tag, right? So we can also just aggregate on the tag node itself. So if I change this actually to the following, I just do an in-between aggregation where I say with t, comma count. Then do the order by limit as inline in my query. So I hope you all know that you can do query. So who doesn't know with and query pipelining at all? One person? So we can talk afterwards. Otherwise, it would take too much time. So in Cypher, you can do inline aggregations, pagination, sorting, and so on, as often as you want, like query pipeline, basically of different query parts. So we do the inline aggregation here, do the sorting and limiting, and then only when we return our 10 nodes, we do the tag name and questions as such, right? So that means it still needs to do the expand, but if you look at the aggregation at the end, it actually says we're aggregating on T, and it only fetches the name of So you see that it now says aggregation on T, and then it only fetches the name here at the very end of the result, which is only means it has to do it for 10 nodes basically, right? Yeah. Whenever you access a property, it needs to fetch the property, except for indexes, but we get to indexes, which is it's a really cool aspect as well. Yeah, but in workflows, if you don't have an index on the property where it actually fetches the data from the index, it needs to read the property as well. Right. So that's why if you have stuff like comparing something on, let's say, user.ssn or book.isbn or product.product ID. If you just want to compare like product A is not the same as product B, you just would say where P1 is not equal P2. You wouldn't say where P1.product ID is not equal to P2.product ID, because otherwise you have to fetch the product ID twice from the store. But actually comparing two products, you can just compare the nodes that they are not equal, for instance, right? So that's actually a good point. I should add this to the slide as well. Good point. And there are some ways of how to limit also these property reads while you're working on expansion and relationship transformation. Is basically you can elevate some of the properties actually to labels and relationship types. So some really undervalued ability of labels. So Neo4j can have multiple labels on nodes, so you can treat them as tags or as roles of a node, right? So if you have a role that's a person, that person can also be an employee. It could also be a developer. It could also be a spouse or whatever, depending on where in life you look at, we have different roles, right? And the same is true for entities in our domain. They have also different roles in different contexts. And if you can elevate some of these roles to a label, you could, for instance, cut down the number of nodes that you look at from like 1 million to 10,000 because you have only 10,000 developers in your organization or something like that. I wish we had 10,000 developers in Neo, that would be really cool. Or perhaps not, I don't know. So that's one thing. The other thing is kind of elevating properties to a label. So for instance, if you have something like a status, like active, not active, deleted, all this kind of stuff, instead of setting where n.deleted equals true, you just move it up to a deleted label, and then you can add a fetch all the nodes that have deleted, or you set a deleted label, or you set a label like processing or being processed or whatever, or status like active, inactive, this kind of stuff is also quite nice for labels as well. And whenever you have kind of countable sets of something that's quite often also in the domain language, right? So if you talk to your business people and they're always talking about these kind of named accounts or so, right? Why don't you add like a named label to your account, and then you can say, find all the named accounts, just match, and colon named, and then that's your named account, and it only has to fetch. Really efficient because there's a different index structure to actually fetch nodes by label as such.
You guys say more than 4 are not desirable.
It depends. So actually, you can do more than 4. It's going to influence performance. It depends again. So because how it stores labels in your nodes is actually, it has 5 bytes to store labels currently, and it uses the number of used bits basically. So if you have 5 labels and they have all just like internal ID 1 through 5, it only uses 4 bits, right? So that you would get 5 by 8 is 40, so you would actually get, what is it? Now I'm lost. You get 10 labels into it, right? So if you have like labels 1 to 5, then you get 10 labels into it because the bits fit in. But if you have really a lot of labels and the internal label IDs are gigantic, then it's actually fewer, and then it has to outsource them. But when you look for labels from the outside, then it actually uses also an index structure where all the labels are mapped to the nodes with these IDs, and then it doesn't matter because you don't need to check against the node. That's actually another good tip that I think also forgot to put in is when you do an traversal, actually I have it probably on the next one. The other one is for relationship types. So for instance, if you have supernodes with 1 million relationships or something like that, which are still a little bit ugly to handle, something that you can do is actually, if you have an important dimension on that node, for instance like a date or a date time, then it can be useful to, for instance, elevate just a year or year months to the relationship type, so you get a substructure, because Neo4j internally stores relationships in groups by type and direction. And if you can split up these 1 million relationships into chunks of 50,000 per year, basically, then of course when you access 1 year, then it just has to access a subset of the group and can read directly these 50,000 at once, which is really good. And if you still want to fetch all, then you can just expand across all relationships type. Or you can actually, in the match clause, you can actually use the pipe operator to say, I want to have here 2010, 2011, 2012, and then you have the 3 years basically. So it's not as elegant as I would like it to be, but it is currently what it is. But we're getting better at this. So Neo4j in the 5x series, hopefully we get node-centric indexes, and then all this stuff will be better as well. Exactly, and the last thing is indexes. I already mentioned that the property store itself is not as fast as I would like to, but the indexes are pretty fast in Neo4j. And what the engine does is basically, when it has to look up stuff from the index anyway, it also fetches the value of the property also from the index. So while you're actually filtering from the index for the node, it also fetches the property value and caches it while the query is running. So if you say, for instance, my query is accessing, let's say, an ID, or let's say I want to do something like fetch my users and sort them by email, right? Then you can say, okay, fetch the users where the user.email is not null, so it can use an index to look up. Then it also uses that index to fetch the property value. And because it also knows that you're sorting by it and the indexes are sorted internally, it also can basically just take the first 10 or last 10 users directly from the index, so it doesn't have to do any sorting operation actually, because it keeps the index sort order. You see it in the profile as well. When you fetch something from index, then it says sorted user.email, and then it actually fetches through the or keeps through the ordering if you don't destroy the ordering, and then you get basically a 0 or no up sorting basically, which is really cool as well. And also in general, if you looked up something where you need to access the properties and you can read them from an index or from a multi-key constraint, then it's easier and faster to read them from the index, and Cypher keeps them around, which is really nice.
Does it matter if it's ascending or descending coming out of the index?
Sorry?
Does it matter if it's ascending or descending coming out of the index?
Fortunately, because they are sorted and there's internal operations to read from the beginning and from the end of the index, it can do either. So originally, when they added it at the beginning, it only has to put it ascending, and then one version later, a few versions ago, they added also descending access, basically. So I mean, it's a tree, so you can navigate it in both directions, but as such. So this is our property read thing. So it uses, so this one had how many? 97 million. So something is, I think I copied the wrong number here. So it uses less data. Relationships. Avoid Neo4j is a graph database. And traversing a single relationship is constant time. But if you have n relationship, it's kind of proportional to the number of relationships that you traverse. So it's still O of n of the number of relationships that you traverse. So while each relationship traversal is constant and it doesn't kind of increase in time, traversing many relationships is expensive. And I was just talking this morning with David, who's doing a node art talk, or did a node art talk. And I said, actually, a tree, like a fractal tree, is a really good visualization of kind of the impact of multi-hop expansion. So imagine you have a graph where each node has 10 relationships, which is not a lot, right? But then you go along like 10 hops, right? So that means it's actually 10 to the power of 10 relationships or paths that you see in your graph that you have to, the database also has to process, right? So if you write, for instance, a variable length query that says, okay, go 10 hops and each of my nodes has 10 relationships, that means if every of your nodes really has 10 relationships, it has to process 10 billion paths, basically, right? And if you then expect this to be 10 milliseconds, you will be disappointed, right? There are things, for instance, if you have a long chain, like for instance, if you created an event chain of like predecessors or next or user journeys or something like that, then it's not a problem because then you have like a singular chain that goes from A to Z, basically. Even better if you have the start and end node and you can say shortest path, then it actually does a bidirectional search. It comes from two sides and tries to match in the middle. And then it's fine, but just be aware. I mean, you also see it in the profile when it says kind of 10 billion expansion relationships, right? So that's also really visible. So, and one trick or one good recommendation for supernodes is as well, don't query across supernodes. So imagine you have a node for country, right? So I had in the demo today like a node for country. And if you would put every like citizen of a country directly on a country node, then the US would have, 340 million relationships, right? So imagine someone says, oh, I want to find all the citizens in the US that are ABC. So it basically would go and, okay, let's go to the US and then expand 340 million relationships and then check 340 million people for X, right? So it's pretty expensive. So what you instead would do is you would say, okay, do we have an index on the properties on the user? We fetch this information, and then just it would actually check against the US node because the user has only a handful of relationships. So it's so much cheaper to check from the user. Okay, is the end node lives in relationship the country US in this case, which is like in 1 dB hit operation. That makes a big difference from that perspective. So if you have the opportunity, don't query across supernodes, but check against them. If you can't avoid supernodes as such, then use the natural structure. Usually in the real world also doesn't deal with these large volumes, right? So you rarely see go and see, okay, I'm going to like a US government page and says, it has like the census data and it says, okay, here's a list with 340 million entries, right? Because that's all the citizens. It would say, okay, we have states, we have counties, we have cities and community. So it has these kind of substructures, and most domains actually have these substructures. Especially if you talk to the business people, they will tell you about like what kind of represents the substructure. So make use of that, right? So you can add intermediate levels, and then oftentimes you can express domain concepts also much better. Sometimes it might be a challenge because there might be multiple overlaying substructures as such, and in principle you could say I can only choose one, but because it's a graph and it's a schema-free graph, you can also add as many substructures as you want to, right? So because you can slice and dice it however you want to, and there's actually some good works by a bunch of people that actually did like these, multi-dimensional star schemas in data warehouses. If you represent this with like multiple overlaying trees in a graph, you can actually really quickly slice and dice subsets of this multi-dimensional space, basically just focusing on subsets of these multi-trees as such. Right. Okay, we already talked about elevating properties to L types. One thing that's also important is get degree. So Neo4j has an internal number stored at nodes that have more than 50 relationships, which holds the degree of a node. So it doesn't actually have to go over all the relationships and count them. And there's also some patterns in Cypher that allow you to get the degree directly. So if you say size of a pattern, then it gives you the degree. I'll show it in the example real quick. So it basically would just read this single number and return it, and then you're done. You don't have to iterate over all the relationships. And the last thing, the two last things is Neo4j 4.3 or 4.4 introduced relationship indexes. So you can now also index relationship type and properties as well, and do kind of global lookups of relationships, which is sometimes really interesting because imagine you have these kind of elevated like year relationship types. You could actually get views of the graph of different years by just saying I'm having an index on the sales 1995, and you just fetch from the relationship index every relationship with sales 1995 globally, and then you basically get a snapshot of the year 1995 basically of the whole graph, for instance, for visualization. That's really nice for if you have like time sliders in your visualization. You can use a relationship index to fetch the whole graph in a few milliseconds basically from the index as such. And there's a trick with the relationship indexes. I talked about the like node-centric thing where you have to elevate stuff to the relationship type. Another thing that you can do is basically to say, I create a relationship index where I also store some attribute of the target node in the relationship, which is then also indexed. So I can actually access subsets based on the source node and attributes either ID or some key of the target node as a subslice as well. So that's a little bit more involved. I just want to mention it, that it's possible. If you want to know more about it, find me later. So to show you the size pattern here, we can actually change this. So currently it does this expansion. So it goes from tag to all questions, right? And then counts the questions. But that's exactly the degree of a tag, right? So along the tagged relationship, that's the degree of the tag. So what we can do instead is the following. Instead of counting these tags, we just say size of pattern. And we don't need question actually anymore. We just need this expression. So what are the incoming relationships to a tag node, right? So that's the pattern that I'm interested in. And this is actually turned into a single value read on the node, right? So and if I run this, you saw that it was also much faster than expected, right? And it still has to find the 50,000 tags. Actually, it's impressive, right? Did you know that Stack Overflow has 50,000 tags? Pretty cool. There are also a lot of like long tail things like, I don't know, COBOL, punch card, whatever things, and it has like 5 questions or 1 question or something like that. And so there's a long tail definitely as such. Actually, we can look at this, right? So you see, like JavaScript has like 1.6 million questions, Java has 1.4 million, then C#, PHP, Python, and so on. Actually, I would have thought Python is much higher up in the data, but interesting. It's probably also a lot of history in there, of course, right? And if we want to sort it ascending, that also would work, and then we would see some of the long tail stuff like. Actually, I don't know why Arrow, perhaps they call it Apache Arrow because the Apache Foundation is really insistent on calling it Apache Arrow. But psychology on Stack Overflow has 0. That's interesting. But there's a different stack exchange for that. But you also see now in the profile that this is actually in this projection. Does it actually say that it calls get degree? No, it doesn't. It used to say that it does here and get degree basically as an operation. I think you still see it in the textual profile. So, oh, that's actually a good point. Let me show you. 1 second. I'm a person which has too many tabs open, as you can tell. So my browser has currently 850 tabs open, and I also have 50 terminals open because I always open new ones instead of reusing stuff. So, so bear with me. That's why I'm also really happy that my Mac has now 64 gigabytes of memory, and SDK use Java 11. What is it? 11.02 open? 11.2 open? 1 second. Because I'm running on Java 19 usually. And Neo4j 4 still. Oh, by the way, Neo4j 5 will go to Java 17, which makes me really happy. So lots of good stuff. What? I just forgot the 11. It's not 11 open. It's I don't know why it does not do the listing. Perhaps it's something network related. Oh, here. Let's see. Let's take. 0.2-open. Oh, thank you. I just use the Zulu here. So if you use Cypher shell, can you read this from the back? Okay, so if I take my query that I just ran here with profile, I just wanted to show you that Cypher shell has also a profile output. We probably need to make it a little bit smaller to not wrap. So you actually see, so this is more like a tabular thing, and it also gives you some additional information, kind of what is a read-only statement, which version, which runtime has been used, and so on. And it used to say here where it says projection, it used to say that this is using getDegree, but it doesn't seem to do this anymore. So sometimes the textual output is easier to put quickly copy from a remote server also, just to show you this. Okay, so this is the getDegree, and unfortunately my favorite syntax for the getDegree, which is this, has been deprecated, and so you have to now use syntax like this. Which is a pattern comprehension, which we'll get to as well. Okay, that's it about relationships. Indexes and constraints. So actually, if we know our domain a little bit better, our Stack Overflow domain, then we would know that there's actually a count property on the tag node. So we actually don't have to use the relationship at all. And we can actually just look at the t.count. And so it does the label scan, reads the properties, and gets this information. All right. And in principle, I also created an index for the count. So in Neo4j, you can create constraints and indexes. Just quick to recap, index are for quickly finding information. Constraints are also for ensuring uniqueness as such, which also have an accompanying index. So whenever you create a constraint, you also get an index for free out of the box. You can do multi-key, so multi-property indexes these days, and multi-key constraints. Which also work for complex where clauses, but they only allow one predicate that is not an equality predicate. So basically, I think from left to right, you can do like equality, like where let's say user.state is Texas, and user.occupation is developer, and user day of birth is greater than X. So you have to do like 2 equality and 1 range operation. That's also supported by the multi-key indexes as well, right? So that's something, because they're internally a tree, and that's why you have to have, like, you can only do 1 range scan on this tree as such. But that could be really useful. So for instance, if you remember Ops Manager that Philip mentioned yesterday, So actually, we were thinking about what are we going to use as a database for storing the events data from Ops Manager for the Neo4j. And I convinced, or we talked with the PM, that we could actually use Neo4j itself for storing this kind of event data, which is not a graph database use case, but they didn't want to add extra infrastructure to store it like another Redis or something like that. And so the fun thing is if you take a node, you elevate the metric to a label, so like something like CPU or transactions also become a label, and then you just store timestamp and value of the metric in Neo4j and create an index. Yeah, then you can do super fast, because it's then just stored in a tree. You can do super fast sub-slices of either by time, by value, and things like that. So it's basically, these are nodes that have a label, or two labels and two values, and that actually fits into one property record, but it's actually stored in the index anyway, so it's all fetched from the index. And so that's not, you shouldn't repeat this because that's kind of not a graph use case, but I wanted to just say it's actually possible to fetch quickly larger volumes of data from an index. As that. Joe?
In the past with other systems I've had, when I've used the index itself, data stored in the index and published it, sometimes it was stale. Is it possible for this to be stale?
No, so Neo4j indexes are all transactional, so they're always updated with the transaction when the transaction writes. The index is also kept in string, so the index is never stale. With one exception, you can configure full text indexes to be eventual consistent. So because full text indexes use Lucene behind the scenes, and it's actually a good question how much time we do have left. It's already 11. I think we should have taken a 3-hour workshop for this, I guess. By the way, what we can do is I can just go down to the dev zone and we put it on the monitor and I continue, and those of you that want to kind of come along can come along. Just to finish the question, so the full text index is backed by Lucene. In the past, Neo4j's Lucene integration had a problem if it's in the transactional path and you have to refresh Lucene while doing the transaction can slow down your write operation. That's why in Neo4j, in the new full text indexes, there's an option to have them eventual consistent. So that's the only place where you have an eventual consistent index in Neo4j as such, right? So I actually didn't realize that it's already 11. Really impressive.
Where can we download the deck from?
I can put it onto a bit.ly link. Let me do this real quick. So I'll do a bit.ly link which is called dev.neo4j.com/ let's say Cypher tips. And I'll put it up later so you can find it perhaps this afternoon if I don't forget about it.